default numbers are dwindling. I'll make sure the topic of this lecture is examined in great detail. But we're getting into interesting things. Today it's finally properly chemistry, so we will be solving things like diffusion equation, Schrödinger's equation, hydrogen atom, and things like that in the next 4 lectures. But for that I need to introduce partial differential equations and the general ways of solving them. But before that, let us begin with something that's actually chemical, and let us derive diffusion equation from chemical philosophy, let us say. So I begin with an example. Let us say we have a beaker, and the beaker has some concentration distribution. It's the coordinate of the beaker, and that's the wall, and we have perhaps dropped a little bit of ink or whatever it was just on the side. And so after a while the concentration of our substance would look something like this. There will be high concentration on one side of the beaker and low concentration on the other. And you know as chemists, and it stands to reason, that the concentration moves in the direction from where it is high to the direction in which it is low, and eventually evens itself out. After a long time has passed, you will have a concentration across itself. The difference in concentrations mathematically is expressed as a gradient. There's a gradient of concentrations here. And so the flux of the substance must therefore proceed against the gradient. So the steepest ascent direction is that way, so we have to move there, but the concentrations move in the opposite direction, and that is actually a physical law. It's called Fick's law, that says the flux of the substance through an isotropic medium is proportional to the gradient of the concentration and happens in the opposite direction. So the flux is denoted J, and it's a vector in general in 3 dimensions, and it is proportional to concentration gradient and has a minus sign. So we have the gradient, remember the number symbol of the concentration, which will be a function of coordinates and time, and then there will be some coefficient regulating the rate at which the substance moves. Smaller molecules tend to move faster, and it has to have a minus sign in front of it. And that is the flux, and it will also be a function of coordinates and time. Notice here that we have 3 things that are perhaps more sophisticated than what you're used to. There is the concentration as a function of 3 spatial coordinates in time. This is called a scalar field because the concentration is a scalar. Then there is the flux, which is a vector, and it's a different vector at different locations. This is therefore called a vector field. And then there's an operator, the gradient, which you have already seen. It is a vector, d by dx, d by dy, d by z, of the 3 derivatives that will be applied to the scalar field here. Okay, so that is the flux. Then, of course, what also must happen is conservation of matter must hold. That is, if something has flown out of a certain area in space, there must be less there. And if something has flown in, there must be more. And in general, let's say if we're looking in 2 dimensions, there will be just a distribution of that vector until, let's say, at some point, we have what mathematicians call a symmetry. That is, there's probably a hole in the vessel, and then the flux vectors all converge in there. And then perhaps if we are adding the substance in there, we've stuck in a pipe and we are pumping the substance into the system, then the flux will start diverging out of that point because we are adding the substance in there. It would be useful to have a measure of this convergence and divergence, and there's actually a differential operator that does it for a vector field, and it's predictably called divergence. Diff of a vector field J is dJx I will not derive it, I will simply ask you to take my word for it that this quantity is positive when the vector field is converging into a point, and it is negative when the vector field is diverging out to a point. Okay, so let us now try and formulate the conservation of matter here. Well, if we are looking at concentration at some point in space, that would be dc by dt at a particular point, r and t. And then, if we have the positive divergence of the flux, like that, then there should be less of the substance at the next point. If we have a negative divergence, that is convergence, there should be more here. So that should be actually minus the divergence of the flux. The change, the local change in the concentration is minus the divergence of the flux out of the location. If something is flowing out, then there will be less of it. If something is flowing in, there will be more of it. Notice, however, that we actually know the expression for this flux, and so we can put it there. That will be minus divergence of minus d gradient of the concentration of R. And let's now think what we have here. Well, d is just a constant. We can take it out, and so there will be just a plus d in parentheses. Then we have the divergence of the gradient. Well, the gradient is the derivative with respect to x, y, and z. And then divergence is actually another derivative. The x component is differentiated again with respect to x. The y component again with respect to y, and the z component again with respect to z. So we actually have a sum of second derivatives here. So the divergence of the gradient is actually the sum of second derivatives. d2 by dx squared plus d2 by dy squared plus d2 by dz squared applied to the concentration. But you have, of course, seen this operator a few times already. It's a Laplacian. I have introduced it a couple of times in different contexts already. And we can therefore abbreviate this equation d by dt c coordinates and time is the diffusion coefficient times the Laplacian operator times the coordinate concentration of the function of coordinates time, and, well, meet the diffusion equation. This governs the transport of substances and heat through isotropic media. This is called diffusion equation. Let's now take a good look at what it is. Well, it has a truckload of partial derivatives. There's a partial derivative with respect to time. Here, there are 3 second partial derivatives with respect to space in there. And so it is utterly unclear how to even begin to solve this, and but we must. And so the second topic for today is how to solve partial equations. So, solving PDEs. I will begin from a rather abstract notion. We don't have the time again to prove this statement, but the statement stands to reason. Let's say we have a function, or a function, a well-behaved function. Well-behaved meaning continuous differentiable integrable with the necessary number of continuous derivatives if needed. Function f, x, y, and so on. And also given basis sets complete basis sets on the space of all functions of just x, g, and of only x, then h, k of only y, and so on. Any such function can be expressed in the following way. We have f of x, y, and possibly other coordinates, will be a sum of some coefficients n, k, and so on, gn of x, hk of y, and so on. And the sum is called k, and possibly all the indices. That is to say, if we have a complete basis set of functions of just x, a complete basis set of functions of just y, then the complete basis set of all functions of simultaneously x and y are actually products of those functions. So not entirely intuitive, but this can be proven in a very lengthy way that this is always possible. Now the wonderful thing about it, of course, is it splits the variables. What we have here is a function where these variables can be interrelated and entangled in complicated ways. However, on this sum, what we have is individual functions of those variables, and hopefully, if we try and solve those equations in terms of this kind of substitution, it's perhaps going to be a little bit easier. So, in particular, if we have some function, and I'll call it psi of x and y, and maybe z, it will be a sum n, k, m, some functions f n, x, some functions g, k of y, some functions h, m of z, times some coefficient alpha and m. So, for example, three-dimensional case. And our task is to find what these functions are. So this is the first little bit of introduction. We can do that. The second little bit of introduction is the classification of these equations themselves. Much like we had the classification of ordinary differential equations, remember first, second order, autonomous, non-autonomous, uniform, non-uniform, we will have a brief classification of partial differential equations because the physics of what they describe actually depends on the type of the equation. So the general form is much the same like any differential equation. You just write the most general possible form of equation that contains all these special cases. So let's say, for example, nk, a and k, d to f by d xm, d xk, where x are all the variables, x1, x2, x3, and so on. So let's just say general second order. Plus perhaps derivatives of lower order equals to 0. What is important here is this a and k. Because it has two indices, it's actually a matrix, and the partial differential equations of second order are classified according to the eigenvalues of that matrix. So the first type, if we have all eigenvalues of the same sign, so all eigs of A of the same sign, this is called elliptic. And it generally describes things like electromagnetic fields. Poisson's equation for the electrostatic potential of a system of charges is, for example, this. Laplacian operator acting on the electrostatic potential equals to minus the charge density at a particular point divided by epsilon naught, the fundamental constant. So this delta is again the bunch of these second derivatives, and the equation is due to Poisson. Laplace's equation in the absence of charges has a 0 here, and there was an almighty feud in the 18th century between Laplace, who was very highly placed in the head of the French Academy of Sciences and so on, who proposed the equation for this was 0, and then Poisson came and said, well, Monsieur Laplace, you're actually wrong. The result was a real big row, and Laplace actually had to die before Poisson was inducted into the French Academy of Sciences. So we do have our views in academia. Anyway, that's Poisson's equation. You can read more about the history of that. Then if we have all eigenvalues of A of the same sign except one is 0, so all of the same sign except 1 is 0, those equations are called parabolic. I think, yeah. And that's quantum mechanics and a lot of time domain processes in physics. So in particular, actually, the diffusion equation here. So notice that there are second derivatives with respect to x, y, and z, and they're all of the same sign, but there is no second derivative with respect to time. The derivative with respect to time is first order, meaning that the corresponding derivative does not appear here, meaning that the corresponding eigenvalue of A is 0, and that's called parabolic. Schrodinger's equation is in that category, and a few other things. In fact, most things that describe dynamics in space-time, so 3 spatial coordinates and 1 time coordinates, are of the parabolic type. And then in here, all eigenvalues are of the same sign except one, which is negative, which is opposite. Is a hyperbolic equation, and an example is the equations that describe the motion of a string of a musical instrument. So, for example, d to u by dt squared is c squared Laplacian u, where c is the speed of sound, speed of light, speed of any kind of propagation, of any kind of oscillations through any kind of medium. So oscillatory processes are described by hyperbolic relations, so that are waves in space-time. And finally, if you have eigenvalues of the same sign all over, they're called super hyperbolic, I think ultra hyperbolic. And those are nasty. They don't have any particular application in real physics because they imply the presence of multiple time-like variables, and we fortunately have only one time coordinate in our dear old space-time here. And then secondly, they are a real mess to solve. So if you encounter an ultra hyperbolic equation in your practice, just stay away and talk to mathematicians. They know how to do it. What we will be mostly dealing with in this course, and in chemistry in general, are the differential equations of parabolic type. If you are unfortunate enough to deal with electromagnetics or electrostatics, more precisely, you will see the elliptics, but as soon as it's time dependent, it drops into either hyperbolic or parabolic. Anyway, so that's the classification. And now we need to solve it, and I think the best way to illustrate how we solve PDEs is to go through a particular example, because I'd say the general mechanics and technology of solving these things is rather horrifying and perhaps too abstract. Let me just pick a particular equation. Let us solve a diffusion equation in one dimension, in fact, for these exact concentrations. And the process of solving that is actually an illustration of the general process of how we solve it. And then, so we will solve the diffusion equation today. We will solve the time-dependent Schrodinger's equation tomorrow. And then we will solve the time-independent Schrodinger's equation in the subsequent two lectures when we deal with the hydrogen atom. Anyway, let us consider a beaker with glass walls. And inside that beaker we will have a solution, and the initial concentration profile inside that solution would be something like that. High concentration in the middle and low concentration on the sides. Or this could be a temperature profile. For example, if we are heating it with a Bunsen burner here, temperature in the middle will be high, temperature in the sides will be low, and in that case our walls would be the heat insulation that is not penetrable to heat. Or a glass beaker with the concentration of a substance. So for example, that's our surface of the water, and somebody dropped a little bit of sugar into it, and it spreads out slowly. Okay, so the diffusion equation in one dimension, that will be the concentration x, this will be -1, and this will be +1, and that will be 0. That's x, let's say centimeters, for example. Our diffusion equation for concentrations will be d by dt, c of x and t. So one spatial coordinate here and one temporal coordinate. And as per the equation we've derived in there, so y and z disappears and we have d, then the second derivative with respect to x, and then the concentration. So d2 by dx squared c of x t. And that's our diffusion. Much like what we had in the case of an ordinary differential equation, we need the initial condition and the boundary condition. Now, the boundary conditions in our case are the glass wall. What that means is the glass wall is impermeable and therefore there is no flux. But that means that if J is 0, that means that the corresponding derivatives are 0, and therefore on both walls we have 0 first derivative condition. d by dx c of xt at x equals ±1 must be 0. Derivative. The wall is 0. It's flat. And then the initial condition, and let's pick some function that describes this. For example, cosine. I'd say that c of x at time 0 was, for example, cosine squared ix over 2. If you plot that cosine, it's equal to 1 at 0, and it's at minus pi by 2 or plus pi by 2, it goes to 0. So nice, neat little cosine graph. And that is our problem setting. We have the equation, we have the boundary conditions, we have the initial conditions, and let us now proceed to solve this. How do we do it? The procedure is called variable separation. And it is based on this statement that I made here. Even though the function might have these variables all entangled and mixed together, we do know that it is possible to expand it like this. So why don't we try and find what these g's and h's are? So we will substitute a trial solution that will be a product of the function of just x and a function of just time, because these are the only variables we have. It's x and t. So we will be looking for a solution of the following form. So try. There is a rigorous proof in the theory of PDEs. We don't have it here because we don't have the time. We're chemists after all. So we say, okay, let us try to find a solution of the following form. F of x times g of t. If we find it, well done us, right? It proves that we were correct. If we don't find it, then something's gone horribly wrong, but I think we will find it. Okay, so take the equation over there and plug that in. d by dt of f of x g of t might be equal, if we are lucky, to d d2 by dx squared f of x g of t. Let us simplify these things a little bit. Here we have a derivative only with respect to time. Functions of x can be taken out because they look like constants to these derivatives. Therefore, what we have is f of x d by dt g of t. Likewise, on the right-hand side, functions of time will look like constant to partial derivative with respect to x, and so we can take gt out of the bracket. d g of t d2 by dx squared f of x. What I will also now do is I will divide the entire equation, so both the right and the left side, by f of x g what this will do is it will cancel g of t here, and it will put it there, and it will cancel f of x here, and it will put it there, with the result that we will only have time on the right-hand side and only x on the left-hand side. So let's continue the process. We will have 1 over g of t d by dt g of t. So f has cancelled, equals to the diffusion coefficient, and I will also, I would say, shift it over here, and that will be 1 over f of x d2 by dx squared f of x. Well, so far so good. We kind of split the variables into pieces, and we moved all things that involve x on the right-hand side and all things that involve t on the left-hand side. Let us now philosophize a little bit about it. This is a very strange expression because the coordinate and the time are supposed to be independent. We can independently vary time in a way that shouldn't depend on the coordinate. So I can put x to whatever I want, and I can put time to whatever else I want. Yet, mysteriously, somehow, they still happen to be equal. There's no way that they can be equal, right? Because that's completely independent from this. The only way this can happen is if these two objects are independently equal to something else, and they have to be equal to it as a constant. So there's no way for this to hold true for all times and all coordinates unless this is actually a constant. That's a subtle bit of philosophy here. Okay, let us call this constant something, and for reasons that will simply just simplify the subsequent mathematics, I will call it minus lambda squared. I could have called it anything else if just the square roots would have appeared and minus would have appeared, to make sure that I proactively destroy all the pesky minuses and square roots. I just decided to give this constant this particular name. It would have been anything else. Minus lambda squared will produce particularly neat and elegant mathematics. Subsequently, okay. So, suddenly, what we have is not one partial differential equation, but two ordinary differential equations, which we actually know how to solve. So writing that out, 1 over dg of t d by dt g of t equals minus lambda squared, and then 1 over f of x d2 by dx squared of x equals minus lambda squared. But that is a system of ordinary differential equations, because that only has x and that has only time. And in fact, all of you have seen these exact equations before. Let me rewrite them in a slightly more recognizable form. We will have d by dt. I could have written full derivatives here by now. G of t is minus d lambda squared g of t, and then d2 by dx squared of x equals minus lambda squared f of x. Who remembers the solutions to this? Kinetics, anyone? First order reactions? That's an expansion. It's a decaying process, right? D by dt of some concentration is minus the decay coefficient times the concentration. We actually know the solution. You've done it many times. That is sines and cosines. Take a sine of lambda x. Take the second derivative of that, minus lambda squared. So that and that we have both already here. Good. So we can write the solutions without too much of a hassle, and let us begin with the solution to the coordinate equation, because what we have in there are actually the boundary conditions on the coordinates, and these will come pretty handy. They are actually the same as so-called quantization conditions. quantum mechanics when you impose various boundaries, but that's the subject of the next lecture. Okay, our f of x has to be trigonometric, or we could have just gone the long and slow way and solved it as a second order ODE. You have all done that in the workshop. You would have solved the characteristic equation, the lambdas, put them into exponentials. Exponentials would have combined into sines and cosines, so we have all been there. Anyway, f of x, once you do that, is 1 cosine of lambda x plus v2 sine of lambda x, where v1 and v2 are those indeterminate coefficients. And if we solve the g equation, well, we know what it is. G of t is an exponentially decaying process. Some undetermined coefficient a times the exponential of minus lambda squared dt. So these are the f and the g's, so we managed to actually find them. Now, they do contain those undetermined coefficients, and we actually have no idea still what this mysterious constant might actually be. As you will see, we will now find it out from this extra information, boundary and the initial conditions. Let us impose the boundary conditions first. Or rather, let us first think about what it is. We have a cosine in here, and cosine is symmetric with respect to the coordinate inversion, right? It's an even function. And within our range in here, we intend the solution to be positive. Sine is anti-symmetric with respect to x, but of course everything here, the initial concentration distribution is symmetric, the differential equation is symmetric, like the second derivative with respect to x. So there is no place in the solution for an anti-symmetric function. So the sine term must vanish. You can prove it rigorously by just substituting the derivatives into those equations, but the quick way is to just philosophize away. So the sine term should be there. More specifically, b2 is equal to 0. Let us now find out what is b1 and what is lambda. Let's put it into there. d by dx of that thing, you see, this is never 0 at any point except infinity. We don't care about infinity. So if the solution is 0, it must be this, that is 0. Okay, so dz by dx, d by dx of x at x equals to plus minus 1 must be 0. Let's write that down. What we have is minus v1 lambda sine lambda x at x equals plus minus 1 must be 0. Well, plus minus 1 doesn't really matter because the sine is an odd function, the minus will just go out in front. B and lambda will cancel because that equals to 0, and so essentially sine of lambda must be 0 for this to hold true. Well, that means that lambda is, where is my rigorous thing in here, pi n, where n is an integer. For lambda equals 0, lambda equals pi, lambda equals 2 pi, the sign goes to 0. And it turns out, therefore, that we haven't actually found just one function there. We have found the entire basis. Remember what you've seen for function orthogonality in your workshop. Individual cosines of multiples of the argument were orthogonal. The same applies to sines. And that is actually the basis in the space of the functions of x. We have f m of x. That is now b1, or we can call it bn because there will be many of them for each individual function. Cosine our lambda is pi n x. And if you check these functions, they are actually orthogonal on the interval -1 to to 1. So through all this messy and complicated procedure, we have actually discovered the basis. What this also means, of course, is that lambda goes into the functions of time too. And that necessarily means that if there are multiple functions f for different values of lambda, there must also be multiple functions g. Now, gn of x will be an, and then the exponential of minus pi squared n squared dt. Well, that's nice because we have found the individual components of our solution, and what now kicks in is this statement here, that the general solution is actually a linear combination of those products. So write the general solution from here. Our C of x and t will be a sum over n from 0 to infinity. It doesn't make sense to do it from minus infinity to infinity because cosine is even, so we'll just be double counting them. An times bn, just another constant, let's call it cn. And cosine pi x exponential of minus pi squared n squared dt. Well, nice, but we still don't know what the coefficients Cn are. But what we do know is that any possible concentration distribution, once it begins, will produce some set of coefficients. This is a system of orthogonal functions on x, so any function of x can be expanded in their linear combination, so that will be our initial concentration, and as soon as we have that initial concentration, it will start evolving according to this equation. But we do have actually a specific initial concentration that's given to us at time 0. It must be cosine squared pi x over 2. Why don't we go and find now these coefficients Cn for our specific initial condition? Let us do that. So we know from there that C of x and 0 was cosine squared pi x over 2. We can rewrite that as 1/2 minus 1/2 cosine pi x, just a double angle formula. And if we write this for time equals 0, the only difference for time equals 0 is the exponential of this. So our C of x0 is a sum for n0 to infinity, Cn cosine pi nx. This is the general form at time 0. This is what we are given at time 0. You can actually see that out of these many coefficients in here, only 2 coefficients are non-zero. The coefficient for when n is equal to 0, so C0 is 1/2, and then C1 is minus 1/2. Or rather, it is C1 minus 1/2. And all other coefficients, 2 pi x, 3 pi x, 4 pi x, and so on, they do not occur in here. They must be 0. So everything else is 0. Therefore, our general solution, or a final special solution for that particular boundary condition and that particular initial condition, is as follows: 1/2 plus 1/2 cosine pi x, and we must add the time term over there, exponential n is equal to 1 minus pi squared dt. And that is the final answer for this. And let us now take a look at what that final answer practically means. If we begin at time equals 0 here, this exponential becomes 1, and we get the initial condition. As expected, that is our concentration distribution rate. When we start clicking time forward, it will start suppressing this cosine. The exponential will begin to drop because pi squared's positive diffusion coefficient is positive. This will become smaller and smaller. It will start suppressing this cosine. What will happen is concentration will start leveling out. So we have the constant and we have the cosine. So it will be something like this. If we give it more time, it will start leveling itself out more. Like that. And eventually, after we give it infinite time, what will happen is at infinity, this exponential will destroy the entire cosine, and we will just be left with the half, and that means we simply have a static concentration across the entire zone. Which makes perfect chemical sense. If you initially had an uneven distribution of either concentration or temperature, it will start evening itself out until it has evened itself out completely. Okay, now that's a lot to take in, so let me walk you through the entire solution process again. The derivation for the diffusion equation is based on a few philosophical observations that Fick made, again, a couple of hundred years ago. He observed that if we have concentration gradients or temperature gradients, they will even themselves out, which means the chemical or the temperature, the heat, will be moving down the gradient. We calculate the gradient, we assign to it the diffusion coefficient or the heat transport rate through the solid medium, and because it moves down the gradient and not up, it kind of smoothes things out rather than sharpens them further, there must be a minus sign. We then reasoned that whatever moves must observe the conservation of matter, and whatever heat transport takes place must have the conservation of energy. And therefore, if we have the flux that's converging to a point, we must get more in there. If the flux diverging, we must eventually get less. So the change in local concentration or temperature must be equal to minus the divergence of the flux. We know the expression for the divergence. I just gave it to you without proof. We know the expression for the flux. We combine them together and we realize that it's actually the familiar Laplacian equation. And that is the diffusion. Okay, I said, how do we solve this? It turns out as a theorem in mathematics, you already know what is a basis set of orthogonal linearly independent functions. We've covered that in the previous lectures. This is in fact why. It turns out, another statement given without proof, that any sufficiently well-behaved function of multiple coordinates can be expressed as a linear combination of products of functions of individual coordinates, assuming those functions are complete basis sets on the spaces of the functions of the corresponding variables. For example, in 3 dimensions, we will have sums of these triples. In 2 dimensions, we will have the sums of products with some coefficients. Any function can be expressed like that. And so it is reasonable to try and find a solution to specific partial differential equations as products of functions of individual variables, because as you saw, after a little bit of philosophy, they split partial differential equations into systems of ordinary differential equations, which you know how to solve. Okay, in 1 dimension, we have a beaker with some concentration distribution. That's the diffusion equation. Only one variable survived in the Laplacian. We have glass walls, meaning no flux, as per Fick's law. If f is 0, then the corresponding derivative is 0. That means the derivative of the concentration is 0 at the walls, which is plus or minus 1. And the initial concentration was a hump, which we chose to approximate with a cosine. Okay, we said as per that expression over there, let's stick a product into this and pull it through all the derivatives. Turns out it splits into that strange expression there, where there's only time on one side and only coordinates on the other. That's called the variable separation process for that reason. And the only way these things can be equal to each other at all times and all places if they are both independent equal to a constant, which I decided to call lambda squared because I kind of knew subsequent mathematics. Okay, then we have two ordinary differential equations falling out of that, and when we stare at them, we kind of discover that we've seen them already. That is first order kinetics, just in case. That is sines and cosines, so we actually know the general solutions. Now, I looked at here and realized that sine is antisymmetric. In other situations where we've got non-symmetric distribution of concentrations, it would have been necessary. But here we only have symmetric distributions, so I'm not expecting any sines. There's a rigorous proof for that, which I kind of skipped, but we can just basically destroy the sign because we don't like it. Okay, we're left with the cosine for the coordinate and the exponential for the time, and the coordinate has to observe those conditions on the walls. It's not just any other cosine, it's a few specific cosines which have zero derivatives at the walls. Once you impose the zero derivative condition, it turns out that gives you the expression for the lambdas, which would be basically no. Lambda must be pi n, where n is an integer. Okay, stick it in there. That's our expressions, and now the only thing that's left are these indeterminate coefficients that convert the general solution to the particular solution. Okay, remember the theorem that we had. There must be products of these functions, and a sum over those products must be the general solution. And Bn times An, since they're unknown anyway, I call them Cn. That is the general solution to our diffusion equation. For any symmetric distribution of concentrations, it's going to evolve like that. But we have a specific distribution of concentrations, which is a half minus a half cosine by x at time 0. I put that general expression to time 0, wrote it underneath, and realized that only two coefficients are actually non-zero, the C0 and C1. So I took that sum, put those coefficients there, and actually kept the time term in the general solution, and that is my particular solution, in which the non-uniformity in the concentration slowly fades over. Yes?
Why is it plus a half, not minus a half?
Well, spotted. Should be minus. I think it is minus in my hand. No, in my handout it's actually plus. So somewhere in there, that should be. Good job. And so that cosine term slowly fades over time and leaves us with the uniform concentration distribution, which is indeed what we must have at E. Any questions? Okay, we will solve another equation of this type in the afternoon.